In our last example, we were looking at a situation where we had two angles and the side that was not a part of those angles. So this angle, and a side apart from those two. So we call it a side angle angle, or you call it angle angle side. Side angle angle, or angle angle side. Other situations may arise where we are given two sides and an angle not touching them. So we call that the side-side angle situation. In these scenarios, we could have either one, two, or no solutions. By that I mean they could either form 0 triangles, one triangle, or two different possible triangles. And I'll show you how that works. In this first example here, we have A and B as our sides. Those lengths cannot change, but the angle in between them, as it swings back and forth, that can change. The angle on the end of them, though, angle A, is stationary. That cannot move. But A, or technically should I say C here, this length, can change. It can be as short or as long as we want it to be. So I'll set it right there for now. B also, as a leg, is set in place because it is set as a length, as well as it is a part of a particular angle, angle A, which means it cannot move. So its end point would be there. We'd call that point C. From C, though, we now have this angle A, and it's set as a length, so it can't go longer or shorter. It has to be the same length, but we don't necessarily know where it goes as the angle, what angle C is. So it can go anywhere. We do know, however, that in this case, we would say that our A value is less than B times sine A. And again, we can just find that by plugging in B and the sine of A and seeing how it responds to our leg A, if A is greater than, equal to, or less than the value of B times sine A. If A is less than B sine A, there is no solution. It would look like this situation where even though it can go any direction it wants, it still will never get to the bottom and complete the whole triangle. So there are no triangles formed in that situation. In this situation over here, again, we have A given, which is stationary. We have length C, which can be as long or as short as we need it to be. B is given as a length and part of the angle, so it can't move, it is stationary. So it comes out to point C here. And then we have our leg A, which again is only so far. Now it can come over here, it can come over here, but it only touches at one point, and that would be right here. And that's because A is exactly equal to B times sine A. When this happens, there's only one solution. There's only one point that will work, one triangle created. There are other situations where, again, if we're given angle A, and it is acute, in all of these situations before, angle A was acute. B was given as stationary, so it comes out to, again, we called this point C. Leg C, though, again, can be as short or as long as we need it to be anywhere within here. And the length of A was also given. Now A has to follow its length. It can go any angle that it wants, but it has to remain that length. And there's only two places, right here and right here, that would create a triangle. So in this case, there are technically two solutions. This solution would work, it would create a triangle here, and it would create a triangle here. And these type of situations only arise when we can say that B is greater than A, which is greater than B times sine A. In those situations, we have two solutions. In a situation like this, though, where A is greater than B, again, we have our acute angle, leg B, which is stationary, comes out to point C. Our length C here, we don't know exactly how long it is, but it can be as long as we want it to be, so that it may be there. And A, which is not as long as B, it's longer. Since it is longer, it won't work anywhere over here or down here. We have to come all the way back around to here. This is the only place where it'll hit and make one complete triangle. So that's a situation where A is greater than B. There are other situations too where A is an obtuse angle instead of A being acute. In this situation, if A is less than B, then there's no solution. In this situation where A is, again, obtuse, A being the angle that is obtuse, then leg A, little a, if it's greater than B, there is one solution. And that solution, again, looks something like this. So you can always tell whether or not we will actually be able to make triangles from this, either 0, 1, or 2 triangles, based on how A corresponds to B and how they both correspond to B times sine of angle A. So in this situation, we want to determine whether or not ABC has one solution, no solutions, or two solutions, then solve for ABC. Now in this case, A is obtuse. It is greater than 90 degrees. So going back to our form here, if A is obtuse, we need to determine how little a corresponds to little b. A is 20, B is 17, so we can say that A is greater than B, which in this case, A being greater than B means there is one solution. So we come back here and we determine one solution. Now, how do we determine what that solution is? This is where that law of sines will come into play. Move this out of our way. Give us a little more space to work. We can say that we have the sine of 118 over 20, because we have our angle and the leg that is across from, equals the sine of b, this angle, so we need the leg that it corresponds with, over 17. Now we just have to solve for b here. If we multiply 17 to the other side, 17 times sine 118 all over 20 equals the sine of b. Now remember, to get rid of this operator, this operation, trig function sine of b, we need to do the inverse sine, otherwise known as the arc sine. So on a lot of calculators, that'll look like a sine to the -1 arc sine of 17 sine 118 all over 20 equals, I could write it as arc sine of sine b, but again, because these are inverse operations, they just cancel out. So basically, we are now just left with b. Oops. So b equals that. We need to punch that into the calculator then, which will determine, rounded to the nearest degree, that we have 49 degrees as b. Similarly, if we want to solve for our c, start up here and we'd say sine of 118 over 20, again, equals sine of 13. And how I got 13 was if we had 180 degrees in a triangle minus 118 minus 49, so minus these two angles here, we'd be left with 13. So 13 is our final angle there. So sine of 13 over c. Now again, we just multiply these things out. We can cross multiply and divide actually. C times sine 118 equals 20 times sine 13. Now divide by sine 118. So these cancel out. So we're just left with C equals 20 times sine 13 over sine 118, which, judging by the calculator, then means that C is approximately 5.1. So now we've determined all of our angles, and we've determined our last leg, that little c. What happens, though, in a situation where we possibly don't have a solution? So in this case, they've already given you the picture, but let's say we did not have the picture, and we just wanted to determine from our angles here. So A is acute. So when it's acute, we have to judge off of B sine A. So B sine A, punch B is 9 and A is 50. So we are looking for 9 times the sine of 50. It's going to come out to approximately 6.9 in my calculator. Well, I guess it's also given to you there. So we have our B sine A, and we know that A, which is equal to 5, is going to be less than B sine angle A, which is approximately 6.9, because there is because A, which is 5, is less than B sine A, 6.9. We know then that there is no solution. We can't really go about solving it because there is no solution, but here is a good picture representation of why. We have our angle, this side length, which is 9, which is stationary, can't really move. C is here. We have our A here. Here's our length A, and it only goes so far, goes 5 units away, but it never touches that bottom there. It can never close up this triangle. That's why there are no solutions for this situation.